In this section, we're going to be going over seismic waves and the Earth's interior. So, how scientists use seismic waves to help discover more information about the inside of the Earth. So, in order to detect um, earthquakes, because sometimes you can feel them, but a lot of times you cannot feel them, when you're further away, scientists use something called a seismometer. And a seismometer is usually a really sturdy platform that's anchored down, and it's basically kind of pendulum shaped, and it has a very heavy, usually a sphere like a ball, hanging here with a needle. And as the ground shakes and moves, this ball will kind of just stay in the same place because it's hanging down while the whole machine and ground is moving. This little needle then will print out or like scratch out or ink out basically a drawing of how much it moved around. And this is called a seismogram. And what's cool is they have these up on land. I've actually heard of these becoming more common, even in people's houses. But they will often go and put these deep inside of the earth to get a better idea of where the actual focus of the earthquake was. So it prints off this like seismogram, and the larger the wave, well, the wave size is measured in something called an amplitude. So a wave like this has a really large amplitude, and here's a P wave that has a very small amplitude. So even though surface waves, that's these waves here, are the slowest waves to be felt or to come, they release all of their pressure at the top of the land, like we said in the last section. And the importance of them releasing all of the energy at the surface or at the top of the land is that that's where all the animals are, the people are, the structures are. So it really significantly affects us here on land. um, so I want to show you something called a time travel curve. And a time travel curve basically graphs the time since the earthquake. So how long it's been since the earthquake occurred, and then the further you are, the distance from the epicenter. And so as you are further away, it actually takes more time for the earthquake to reach you. So if you're only a thousand kilometers away, maybe it only takes 4 minutes in this. Or if you are for the S wave, for the P wave, it was maybe 2 minutes about. Okay, but if you're 5,000 kilometers away, it maybe took you 7.5, or is that 8.5? Let's see, that's 8.5 minutes to have the P wave reach you, whereas it took 15 minutes for the S wave to reach you. So these waves, because the P waves will travel and hit you faster, the further you are, the further apart these times will get. So I think that's basically what I wanted to show you there. But I have a cool animation here from IRIS, and they're really good at making little earth science animations. So in this one, I want to show you that they have an earthquake, and they have the P waves in red, the S waves in like a blue, and surface waves in yellow. And as they release it, you can see like the P waves finally hitting, the S waves hitting later, and these surface waves traveling along the surface, right? Now it's going to rock the cow. And I like how it says here, all scales are exaggerated. So like a cow is not this big compared to the earth, which is good because we would not have any space for anything but cows if it was. Um, so basically, as it travels along, I want you to really notice how the P waves on this house A. So look at house A and watch how, because it is so close to the epicenter, the P, S, and surface waves hit really close together, and then they're really spread out compared to like how fast they hit the D wave. So watch house A here, how fast one type of wave after the other just hits it. So we're waiting for that earthquake still. And then here we have that fast. It already all hit. Okay, so we're going to look at that again. And we have the earthquake P, I can't even say it enough. PS, and then the surface waves hit that quickly. Okay, so now I'm going to back it up and let's look at house B. Okay, house B is just now getting hit with primary, now secondary, and now surface. Okay, let's look at let's look at D, because that's going to be the most exaggerated. So here comes the primary on D. There's the primary. Surface never got here because they had to go through the core, and we'll talk about that in a second. And then here comes the surface waves at the end. And so the secondary waves died off on that one. Let's look at house C. Here's the earthquake, and the primary waves are just now hitting C, then the surface or the secondary waves. And here comes the surface. It's got to get the cow first, and then the house. So you can see it hits primary, secondary, and then the surface waves. Okay. So the important piece about that is that, and I want to mention, like, back up and, well, it's a kind of moving forward onto this chart. Knowing how the waves, different waves, travel through different different substrates helps us to know what the inside, the interior of the earth is made of. So the rate by which an earthquake wave travels tells us what kind of substance it's going through. And for example, an S wave goes up and down. And S waves, like an up and down motion, doesn't move through liquids. So that led scientists to believe that because S waves just kind of give out at a certain point in the Earth's interior, and then they pick up again. So maybe there's S waves here, no S waves here, and then they'll pick up again up here. Led scientists to conclude that part of the Earth in the middle was actually made up of a liquid, since S waves cannot go through a liquid. Now, P waves can move through a liquid, but they do bend as they go through. And that's exactly what happens to P waves when they hit the outer core of the Earth. So both P waves and S waves will travel through the mantle, but P waves will bend or refract as they hit the outer core. So basically, by the way these waves are moving or traveling differently, and scientists watching this, scientists can learn about the density and composition of the Earth. And not only can they figure out what it's made of as far as solids or liquids, scientists can also make some good inferences about what the temperature of the Earth is. So hot things are usually less dense, and cold things are usually more dense. So this is a cutout, cutout from a piece of land in Japan. So going into the Earth, like a cross section out of the Earth in Japan. And scientists can see that waves will travel very quickly at certain points, and then, you know, at a very medium rate, and then very slowly through certain points. And you can see here that when the waves are traveling very slowly, it's very hot. At a medium pace, like orange color, that means it's going like at a medium pace, and it's a medium temperature. And Where it's very cool and dense, it moves very, very quickly. So it helps scientists get a good idea of what temperature the Earth is in different places as well.